So am I audible? Hello. We'll start 3 to 4 minutes. Okay, let the persons join. Yes, am I audible? Hello. Hello. If my voice is clear, any one of you can just confirm so that I can proceed. Yes. Hello. Yes, am I audible? Hello.
Yes, sir.
Yes, sir. Yes, now am I audible? Yes, hello. Okay, so I think no problem with the audio, so I will just go ahead. So any of you, so if any of you have any problem, then you can just ask me. So any doubt from the previous week? Yes, you. If you guys have any doubt from the last week, you can ask. Any doubt while solving the assignment problems last week? Okay, so before starting the session, one thing I want this session to be interactive. If no one of you answers or responds to the queries, then or asks any doubt, there is no meaning of this live session, right? Because I will be speaking one way and you will be just listening. This is not an interactive session. So this session is intended to be interactive. So maybe you can just everyone if you of you can if they can turn on the video and ask doubts, that will be good and that will be encouraging for me also. If all of you can turn on the video, I will be happy. Then we can have an interactive session, right?
Hello, sir. Sir, good evening, sir.
Yes.
Did you hear
Good
me?
evening. Yeah, yes, you are
Sir,
audible.
myself, I need a little bit clarification
Yes, yes, yes.
regarding we
Sir,
have two
it
forms,
will be
sir.
good.
One is
Yes,
a
yes.
Cartesian form, other one is polar form.
No, no. Okay, I will explain. Just, but that before that, if all of you can turn on the video, it will be good. We can have an interactive session, right? Because I will be speaking in one direction and you will be listening. That is not good, right? If you can all of you can turn on the video, that will be good. Because we can have an interactive session. You can also solve with me and get the clarity. Otherwise, it is of no help, right? Only seeing the recorded sessions will not be helpful. Okay, so okay, carry on with your doubt. Yes, go ahead. Yes.
Hello, sir.
Yeah, go ahead.
Sir, we have two forms. One is a polar form and other one is Cartesian form.
Yes.
We always represent current in polar form.
We represent
I am correct,
all
sir?
the yes, we represent all we can represent any AC quantities because the
All the
AC
current, uh,
oh yes, yes. All the currents, voltages, all that
no,
we can even the power also we can represent in polar form. Because wherever we have
yeah,
but polar is a encoded version like a vector only, but it is rotating. Rotating in space means in time it is having some variation. So why polar we need? Because we want to
yes,
embed two information. But to information we want to embed magnitude and phase information. Any sinusoidal quantity you have two information. you need to have two information. One is
Yes,
the
sir. Yes.
amplitude and one is the phase. Another is the frequency of
Yes, sir.
oscillation. But assume that in the space, all the parameters denoted in the polar notation are having same frequency of oscillation, or the
Okay, sir.
AC frequency or power frequency. So then you
In
can just
exam also we have to represent in a polar form.
yes, yes. See, where you represent in polar form is just see. So the polar form, where you use polar form means you just have any signal and you have associated it with some theta. So assume a circle like this,
Yes, sir.
and you have the argand plane, and there you can use two notations. Okay, so one notation you can use is the polar notation, where you have the s angle theta notation, where all are assumed to have the same frequency. All parameters or signals we will be denoting in this plane will have the same omega. So for that same omega, if you have two information, which is s and theta, then you can represent any sinusoidal quantity. So we can denote it in one way is the polar form, or you can write it in Cartesian form. What is Cartesian form? Same like this. So it will have one x and y. So this we denote by plus j. In maths you denote by plus I. So it is same only. So s cos theta in the real plus some j into s sin theta, and theta is omega t. T is the time. So why two forms? Because polar form helps us. So it helps in multiplication and division. Multiplication and division of two AC quantities, whatever you are assuming the signals. AC signals I can write. And why Cartesian form? It is easy to add or subtract two different signals in this form. So that whenever we are doing some complex calculation in power or in finding the voltage rating or current rating, we can use polar forms in the determine the power. Because what is power? Power is root 3 into VL into IL into cos phi. You see, na, two signals like these are getting okay. We are doing it with amplitude and then determining the power. But what if you are asked to find the real power? You need all the amplitude as well as the phase information. So all those information you need to find the power triangle. Then only you can determine the reactive and active component. So both are important. So during product or division, find out even the current also. See, you determine current as voltage power by voltage. Then also you need the angle information to find the current, or current is also V by Z. Then also you need the angle information. So during this kind of operations, your polar form is very helpful. So no one will tell you to do it in polar form or Cartesian form, but you need to know when to use what form. So in those conditions, your calculation will become easy. Otherwise, you have to again convert from polar to Cartesian and then do and again transform to polar to give the answer. And polar will also directly give you the amplitude. In Cartesian, you have to break it and then again do the reverse operation to find the amplitude. But polar, you find the amplitude directly. This is the amplitude of the signal. So these are quite advantages over the Cartesian form during such calculation. So that's why we use in polar form. It is not any hard and fast rule that current you use polar and voltage you use Cartesian. Only during the type of operation you are doing, you are accordingly changing your transformations such that you can easily calculate and give the answer in the least possible time. That is the only philosophy behind that. Okay, so any more doubt in the problems or in the concepts we just covered up to that point, or in solving the assignments, you can just ask. Otherwise, I will just go ahead with the problems. Shall I go ahead, or you have some doubts? Any one of you, if you have any doubts in some concepts or anything, you can just ask.
Yes, sir, we will go ahead.
Okay, okay. So the continuing from where we ended the last week, I gave you one problem as homework. So any of you solved that? So the homework was easy. Simply we just what we did, ZL was 15 plus J12, and for that we got these answers. I hope you remember. So it was a simple problem of a single phase AC supply, rated voltage 220, and we had the source impedance 2 ohm and 4 ohm inductive reactance. And I told you in the last problem that ZL was 15 plus J12, which was a reactive load. And now you are realizing a synchronous static series compensator to elevate the voltage and maintain it rated, which is 220 volt. And we asked you to calculate the minimum rating of that compensator, and also in stages we asked you what was the current rating, voltage rating, and then accordingly after that the volt ampere rating for 15 plus J12. That is a lagging kind of load. Now you got some answers for that. 47.73 was the current voltage rating. Sorry, this is voltage. Okay, and this was the current rating, and volt ampere rating was 546. So this was the minimum volt ampere rating. Minimum volt ampere rating, we told you that we had no control over the power factor, and for such cases, because we have the effect of source impedance, and I am not specifying any power factor, only I want the minimum rating of the volt ampere of the compensator. So we lost control over the power factor. We cannot maintain unity power factor in such condition, and assuming that, I want to go ahead and calculate the minimum volt ampere rating. So you can find it geometrically also, which we have some forms of that, or you can use the power balance technique to directly calculate the minimum volt ampere rating. But in such condition, we assume that we have 15 plus J12. So I told you, will there be any change for 15 minus J12? That is a leading kind of load. So that was the problem I gave you as homework. So any of you did it? Just answer me one simple question. Will there be any change in the current rating of the compensator?
No, sir.
Current rating?
No, sir. No, sir.
No. So what will it be if someone asks you what is the current rating of the compensator? You will simply, for part A, what you do, just assume that it has been compensated, and during that operation we are asking you what is the current rating. So then you IC rated will be same like rated voltage, which is the amplitude of the voltage, divided by ZL. Mod ZL for 15 minus J12 or 15 plus J12. This was the 15 plus J12 case. Lagging load, I can say. And this is the leading load. So both are same. So if you find mod ZL and 220 by mod ZL, it will come same. It is 11.45 only. 15 square plus 12 square. And then root it over. It is 19.2, and 220 divided by 19.2 is 11.45 amps only. So it is same. No change in the current rating. Now tell me, will there be any change in the voltage rating for 15 minus J12 compared to the earlier case of the 15 plus J12? Can any one of you tell intuitively without solving? Yes, I want to hear some answers. Any intuitively you can tell what is the action that this synchronous static series compensator is doing? What is the main purpose of installing a synchronous static series compensator for such type of loads? Actually, this is the, I think you know the topology. We have a single phase AC supply. That is, we have this AC mains, which is 220 volts, and we have some RL source impedance, which is 2 ohms, and this is J4. So this is a source impedance, always inductive in nature. Okay. So after this point, you are connecting this compensator. So I denote it like this. And then you have, I am drawing a single line diagram only. So you have the load PCC, where you actually want to make the voltage equal to the rated. And here is the point where the loads are connected. So ZL. So ZL is given to be now 15 minus J12 ohms. So where we are talking about maintaining the voltage or regulating the voltage, it is at this point, right? So this is the point we are talking about. So can you kindly tell me what is the action of this of installing this kind of compensators here. What will the compensator do in this case for a lagging load or for a leading load? So who is defining the load current here? The load, obviously. The load is now leading kind of nature, and previously you have had a lagging kind of load. So the type of load current, the nature of load current that was flowing in the circuit previous to the compensation, assume it was not there in the picture. So the nature of the load current that was initially existing will define what kind of voltage you would have got at this load PCC without the compensator doing its work. And after you install the compensator, its only job is to compensate for that particular voltage drop such that it goes to the rated. So the nature of the load should have a implication that you can intuitively tell, because the nature of the load will define the nature of the load current. The nature of the load current going through the source impedance will define the nature of the voltage drop. The nature of the voltage drop will obviously guide or govern what we actually want to push to actually want to compensate for that drop, because your aim is to compensate for the drop in amplitude. So if your current amplitude is varying, current amplitude is not varying, your current phase is varying angle, and that with along with this source impedance will push a different kind of voltage. So you want to compensate for that voltage, and that is your intuition that it will be the compensator that you actually installed will able to compensate for that voltage, and you get rated voltage. So just let's draw the phasor diagram for this. Okay, with the phasor diagram. So let's draw for two cases. So this is leading load and this is lagging load. So lagging means 15 plus J12 kind of load and 15 minus J12 kind of load. So we took the reference as the source supply PS, both the cases. And before compensation, tell me what will be the current, how the current will be, because in the 15 plus J12 case, before compensation, your current was lagging in nature. But also note, you have a source impedance in both the cases. So note it that it is 2, or what was the value of the source impedance? 2 and 4 ohm. So 2 plus J4 was in all the two cases. You are having the source impedance present. So here I can say net impedance is reactive only. So if someone asks you what is the phasor diagram, what you can do is you just calculate. So one thing I can write from here that the load current is of lagging nature. So this is the load current. And it is very easy to find before compensation. You just divide the voltage with the net impedance. You are having this kind of nature of current. So VS, now after compensation, someone told you that it is unity power factor, right? Also, this information is also given in both the cases. But since you are aiming to do minimum volt ampere rating, you will not get unity power factor. So it is in your hand that what you want to achieve. If you want to achieve unity power factor, you will not get minimum volt ampere rating of the compensator. That I already discussed the previous week also. So here, no unity power factor is operation is there. Only minimum volt ampere rating we want to push. So we are drawing this phasor diagram for minimum volt ampere rating in order to achieve minimum volt ampere rating. We are not fixing any power factor that we want unity power factor and then we are doing not like that. We want to achieve, our main aim is to minimize the volt ampere rating of the compensator for this particular case, and for this also is the main aim is to achieve this minimum volt ampere rating of the compensator. Okay, so in this case, tell me VS and you have IL of this nature. So what will be the actual voltage appearing across the load? It will be VS minus the drop across the source impedance. So what will it be? So VS minus IL into RS, and IL and RS are all IL and IS are all the same because it is a series network, as you can see in this topology. Whatever is the current, this is flowing to the compensator only. So your IL and IS are same, and this is denoted by small letters. Okay, and this, since we are drawing the phasor diagram in the RMS, we are denoting by capital letters. Okay, so Vs minus IL into Rs will be like this. Okay, small drop because Rs is actually small. So this is Vs or Is into Rs. So this is the drop across the source resistance, and minus J into Is into Xs. This is the drop across the source impedance. So your voltage will look like before compensation, I am telling. So this is VL before compensation. And as you can see also, some small portion is drop is there. Amplitude, speaking in terms of amplitude, this amplitude of VL is somewhat less than Vs because the inductive kind of effect. So drop is there. Now what you want to actually maintain rated amplitude of voltage across the load. So I also explained the last week also that to achieve minimum volt ampere rating using the compensator, what is the smallest possible rating you can push? This may be the smallest possible voltage you can push to maintain minimum volt ampere rating of the compensator. So this voltage, if you can just inject, you will achieve that minimum volt ampere rating condition. Up to this is clear. So this is V comp. And after you find V comp, you can just maintain the voltage and the load will accordingly draw the current and you will achieve that minimum volt ampere rating. So what this angle is actually, if you can go with the nomenclature, this we call the load power factor. Why load power factor? Because this is the angle between the load voltage and load current. Why load voltage, load current? Because this line what we are denoting, this line is the load voltage line. Don't confuse this with the supply. So this is not the supply voltage line. So the difference between the two, we denote it as angle power factor. So this is only the load side power factor. And if someone asks you what is the supply side power factor, what will you tell? This is the angle between the, note that this is also Is because we are series network. So voltage and current source side, this is called beta. So this is the source power factor. And generally we denote the angle between the two, the shifted angle due to the drop, and denote it by delta. So these some common terms you must have heard also in the lecture. Is the delta, because this is the shift, and since power is flowing from source to or supply to load, you can see the delta of this Vs is higher than, or the angle of this Vs is higher than the angle of the load. That's why the power is flowing. So delta is like this. Now also intuitively you can see in this phasor diagram also that if this what you say, this VL, this VL is governed by this lagging nature of the source impedance as well as the load. So now what you do, you just replace it with your leading kind of load. Okay, so this will be IL of same amplitude, and this I can tell as theta. And what is your source impedance drop? This is Vs plus IL in minus IL into Rs. So this will be like this. IL is Is. And this is minus obviously. So it will be like this. J into Is into X. So this is the VL. So what the compensator has to do? In order to maintain rated voltage, it has to actually inject negative voltage to actually reduce the effect of the increment due to the leading nature of the load. So the load actually plays a quite important role, as you can see. Before, the voltage to be injected by the compensator was this much. But in this problem, you see that since the load is of leading nature, if I draw the leading load and then do minus is into rs and then minus j into xs, so then it will come more than the amplitude of vs. So you need to inject some opposite minimum only, but this amount of voltage you need to inject. So it is different, and so that this minimum VA rating is achieved. So let us calculate. Actually, these two are the phasor diagrams that you can apprehend for these two cases, how the compensator needs to perform, how the series compensator actually needs to push the voltage to make it somewhat different. So now let us go and actually determine the what is the voltage that it has to push. Is it different or same? It will be clear. So let us calculate just like the previous week. Because this was interesting, so just I thought we cover this also, because in the exam you may be asked like this. So same steps if I have to do, and then you have to calculate. Okay, so anyone remembers how to calculate that voltage for minimum volt ampere rating? What is the traditional step that we have followed to calculate the voltage? Actually, current is very easy, I told you last week also. But voltage you have to do power balance for minimum volt ampere rating. If it is not mentioned minimum VA rating and some power factor is given, it is easy. One line problem. Power factor from power factor you can just calculate using that rule that voltage pushed by the compensator is nothing but VL minus VS. But it is not that direct. Geometry comes into picture in this case. So you do power balance and you write the expression. So anyone can tell me what I write the expression? So power balance means that we have to balance the active and reactive power, right? So let's do active power balance first. And before that, I just write the parameters that I know. So just like the previous week. So RS equal to 2 ohm, XS equal to 4 ohm, or you can write J4. But since we are talking about only the amplitude, I write the amplitude only. And RL is what? 15 ohms. And XL is 12 ohms. And your IS is 11.45. And theta is the power factor angle. So power factor, how will you calculate for this? This is the load power factor we are talking about. So theta you accordingly put, because theta is what? Theta is load power factor. Load power factor, how we determine? This is tan inverse of 12 by 15. What is it coming? Just check. It is 38.65.
38.65.
But since the from the load voltage, your current is leading in nature. See in this phasor diagram also. Why up that phasor diagram? So since the current is leading from the load voltage, your angle will be positive. Okay. Theta is plus 38.65. So remember that it will be useful. So theta is plus 38.65. And what is the next one? So if I can write is cos theta, what it will be? Just like the previous week also we calculated, it is 9 amps. And is sin theta amplitude is 7 amps. And source voltage is 220 volts. Now just do the active power balance. So what is the active power balance? So active power balance means the voltage across the supply and the supply current, which is same as the load current for this case, into cos beta. This is the power delivered from the supply. Plus some power is coming from your compensator, which is VC into I supply into cos theta. This is equal to the power dissipated actually across the load and the source impedance. So same equation will come here. And another equation is coming, Vs into Is into sine beta plus Vc into Is into sine theta equal to. So the compensator in this case, you need to analyze whether it is pushing active power or pushing reactive power. So accordingly, and Is squared into Xs, and now what I will write is XL. Previously it was XL, okay. Now it is XC because we have some negative portion of this impedance, na. This XC. So this what it does, it pushes reactive power. So if I go ahead with the convention, first convention was you are pushing something, supplying. So I write it in this side, and you are absorbing here. So I write plus on this side. Now what it was doing, source impedance was absorbing this side, but this will Is squared into Xc. This will be negative because whatever load was there, it was supplying some reactive power. So in the previous case, we were doing plus. In this case, you were doing minus. And also think of one thing, because we don't know actually what will be happening. So I just kept it plus, assuming your compensator is supplying some reactive power. Now you just solve it. And so what are the two unknowns? Two unknowns are beta and this Vc. So beta is one unknown. Is beta, and another unknown is Vc. So what you need actually Vc for this leading case. So you can get rid of beta. How to get rid of beta? You just square and add, beta will be eliminated. So what is this? Vs into Is, right? So Vs is 220 and Is is 11.45. So 220 into 11.45 will come. Two five one nine, right? So 2519 into cos beta plus 2519. So Vc is unknown. Vc into Is cos theta is 9. So 9 Vc equal to Is square into Rs plus RL, that you know already what it is. So just we calculated also the previous week. So 2228 was the answer. So I just can do Is square RL plus Rs. 17 into Is square is 11.45 square. So 2228, okay, it is the correct. And then the next one was Vs into Is, which is 2519 into sine of beta plus, assuming that it is delivering some reactive power, we don't know yet. So what it is, Vc, and Is sine theta is 7. Theta is the load power factor angle, please remember, and this is the supply power factor angle, which is unknown, still unknown. So because we are considering minimum volt ampere rating, and hence we are denoting the theta. Theta we know, theta is plus 38.65 given in the problem. And this side you know that at least the load is of capacitive nature, or whatever you tell, leading nature. So it is pushing some reactive power. So you just write what will be the Xs minus Xc, what it is coming, just anyone do it. So 11.45 square into Xs minus Xc, right? So Xc is 12, okay, not XL. Here you don't have any significance of XL because Xc, because we denote negative J in impedance by Xc, okay, capacitive reactance. So 4 minus 12, it is minus 1048.82. Up to this, everyone have done with me, right? So they are getting same answer. Tell me if there are some calculation mistakes. I will do it. 11.45 square into
Yes, sir.
X minus XC. So this is, I think, correct. So then you just find out what is, so what it is coming. So if I square and add, take it this side, 2228 minus 9 VC whole square plus, I can write minus 1048.82 minus 7 VC whole square can be equal to 519 whole square. And just now what you need to do, you just can solve for it. But did you notice some difference? This with the previous problem, this term came different. All were same. This term went different because the XC, the leading load, was helping in pushing some reactive power. So this term got different. This voltage term. Here, the main difference came here. Because this we did not know what was the compensator doing. Because still it is geometrically it can be interpreted, but in the algebraic equation we did not know. We left it like that, assuming that it was supplying. But the load was also supplying the reactive power. So it itself was helping it to elevate the voltage. So inherently, if you can intuitively tell that this compensator will now behave as an inductor, sitting there as an inductor. So the job of that compensator sitting there as an inductor will be further to decrease some voltage, such that that increment in voltage will be adjusted and rated voltage of rated amplitude can be maintained. So that was its role. Previously, it was sitting there and pushing some reactive power, as you saw in the phasor diagram also, to elevate the voltage. But now the voltage is already elevated by the nature of the load. So it was just sitting there, inserted between the series network and trying to reduce the voltage level. So accordingly, you can see the VC will come out to be different, as you can also understand intuitively. So that was only thing I wanted you to see, because the nature of the load will actually govern the volt ampere rating, the minimum volt ampere rating of the compensator. So that was the only observation that I wanted you to see. So you can calculate the VC value and it will come out to be different. Anyone can just solve and let me know. So solve this and you see that VC value will be different. I can use some solvers also to calculate this quickly. So this minus sign can be neglected because it is inside the square. But whatever change it has to do, it has already done in this factor 1048.82. So VC will obviously be different. Let us calculate what is VC. You can calculate and just. So will you be able to calculate? Because it is simple. Just solve the quadratic equation and check. So I will go ahead with the new problems. But just I wanted you to see this difference. That load actually differs, makes the difference of the rating of the compensators to be used. So if anyone can do, I can wait, and then we'll move on to the next problem. So I can maybe also solve it. I hope I can remove this part. Okay. So this was reactive power balance. And now you can just go ahead with this equation. So I will rub the top part. So try to solve this equation. 2228 minus 9VC square plus 1048.82 plus 7VC whole square equal to 2519 square. So just solve this. So two roots are coming. One root is minus 6.86 and one root is this. Which one I will take? As expected, I will obviously want to inject the negative voltage to reduce the increment in voltage by the nature of the load. So this is true. So can you see some observation? First note up to this. If you are done, just let me know. This you can plug it back to the first equations, first two equation, any of the first two equation to determine what is beta. Just see these things, you will get also intuitively you should be able to think what it should be. Lower or higher, I mean, not exact value. So you saw something? See this. How much burden was there on the compensator when it was lagging nature of load? It has to push lot to elevate the voltage level. But now see, the burden on the compensator is reduced. Burden means I am talking about the reactive power burden, because the compensator is here to elevate or decrease the voltage, or so it is nuclear and reactive power, right? So this is very less compared to the previous case. So accordingly, the rating will also reduce. DC into IC, that is the volt ampere rating in this case, which is a totally different case because the load has changed. So 6.86 into what was IC? 11.45. So very less. The load is helping itself to actually build up or make up for the drop in the voltage amplitude due to the source impedance. If there were no source impedance, there wouldn't have been any drop across the load terminals, right? But all the action comes due to the presence of source impedance here. So accordingly, you can just determine the volt ampere rating. That was one thing I just wanted you to see, that how much difference it can happen just by the current rating remains the same, but the voltage is actually changing. That was the only thing just I wanted to explain. So just move on and see this next problem. That same kind of problem, but little different. So just note we have a self-supported DC bus. So anyone can just remember, I just explained what it meant by the term self-supported DC bus of any kind of compensator you use, DStatCom, whether it be DStatCom or some UPQCs or. So what is the meaning of self-supported DC bus? I told you it has some limitations. So the meaning of self-supported DC bus is that whenever you have some self-supported DC bus within a compensator, it cannot push any active power. It can help in mitigating the reactive power requirement up to its rating for which it is designed for. That much it can do, but it cannot help to push any active power because you are not connecting any active power source at the DC node. So it cannot push any active power, simple by power balance. So the self-supported DC bus means that it is drawing some amount of power to maintain that capacitor voltage, and hence it is self-supported. But no DC sources like PV, that is you don't have any solar or battery or anything like that connected at the DC side. So from whom it will take the active power? There is no one. The only source is the supply. Supply is actually building the DC link voltage, but your active power is only made by the, that is whatever is the active power demand. Your compensator will not come into picture in mitigating that. Only your compensator will work for whatever reactive power requirement you need through proper control actually, because all these compensators are working through proper control, because these are all converters and needs to be switched. The switching pulse needs to be generated accordingly as per the control, whatever is your aim, whether you want to maintain some voltage or want to compensate for some power factor requirements. Accordingly, you can just select your compensator and then generate the switching pulses for that. So, but one thing is that you need to know that the self-supported systems don't have any active power sources integrated within them. So that will also be helpful during the exams also. So that just note this term, okay? And then go ahead with whatever process we had followed. That note that is a three-phase system also, because you sometimes forget, because we have been asked to calculate the volt ampere rating and someone was asking the doubt that what was the volt ampere rating, whether we'll multiply by √3 or 3. So we'll just took the three-phase example such that you don't have any doubt. We'll do it for calculation for such systems are always in per phase basis, but then at last we'll mitigate by incorporating the three-phase system. So just the single phase equivalent circuit we want to. Previously also we drew the single phase equivalent circuit only, a single line diagram what we drew, and then we go ahead with the three-phase calculation. So you must be understanding that whether when it has not been specified anything, then the three-phase system is obviously a star connected system. So the start, no one will tell you like this differently in the questions. It is self understood that it is a star connected system. And what is this voltage? Because this voltage was also asked that whether it is peak or RMS. So this is a 400 volt RMS voltage, line to line. Okay, this is not phase volt. So this to be understood in
Excuse
every
me, sir.
problem. Yes.
Sir, are we covering UPQC problem today?
UPQC problems I am covering, na. After that only UPQC will come. This after this only.
Okay.
Because this one was 3-phase. I think you only asked me the doubt in 3-phase how to calculate the volt ampere rating. For that I took this problem. Okay. So this one we are trying to solve. We'll go ahead step by step, no hurry, because I think I have covered UPQC problems also in the last week. This week also we'll be covering the remaining variants. So it will be complete. So if you do with me, it will be more fast, right? So I'm explaining said that you guys don't have any doubt in solving later on. So just go ahead and then we can speed up at the end. UPQC will be covered today only, okay? We're done. So how will you approach this problem? This problem, what is the aim? You have to do what? That raise the voltage same as the rated. So this kind of problem we have tackled, just only the 3-phase term we need to actually understand. So try. How will you do? And no one is telling me the approach. How will I proceed? Tell me. Because we already did it last week also, na? Only difference is that it has a self-supported DC bus. Nothing difference is there, na? So you should be able to solve. Just anyone start. How will I start? Let me know. So what is the system? The system is like this. I have a compensator here, and then I have the load. So this is the system. You can tell. This load is 24 plus J18, and this is 400 by root 3, na? That source impedance is also there, 2 plus J4. So the first step which you need to do is calculate the current. So what is IL or IS, I can say. So voltage by net impedance, right? Is 26 plus J22. So what it is coming? So Z total is actually ZS plus ZL, na? Is 26 plus J22. So what it is coming, just write in polar form. Anyone was having doubt in the polar form, can he tell me what is the this when converted in polar form? Just calculate and let me know what is this converted to polar form.
Sir, 34.05 with an angle 40.23.
So how you did is that, like, you just assume this is 26 and plus J go on top, this is 22, and you are asked to calculate this amplitude S and this theta. So by using Pythagoras theorem, you just do 22 square plus 26 square, and when you are asked to find theta, it is tan inverse of, since it is in the first quadrant, so it is tan inverse of plus 22 by 26, which is coming out to be 40.23. So this is correct. So now you know the Z total is 400 by root 3 divided by 34.05, right? This 6.78 angle. What is the angle? This is minus minus 40.23. Yes, so IS I calculate as 6.7 angle minus 40.23. And what is after compensation? Because I know after compensation voltage is maintained to rated, so I can calculate. This is after compensation. So voltage is same 230.94, which is coming by 400 by root 3, because it is now maintained after compensation, divided by only the load impedance. Load impedance is, but how much is it load? 24 square plus 18 square root over 30, right? So 230.94 divided by 30 is 7.69. So this much is after compensation. So if someone asks you what is the value of source current after compensation, this is the answer. But what is asked in the problem? Asked in the problem is volt ampere rating. So you have to do power balance. Because you are not mentioned that you have to maintain unity power factor, so you go ahead with the power balance, because nothing is mentioned about power factor. When nothing is mentioned about the power factor, please be careful of such kind of problems in the exam also. And they will give you short problems only. So don't worry that you have to do so many steps. Only the crisp of the problem you have to grip and then apply only those equations, whatever we are discussing here. So whenever nothing is mentioned about the power factor, they are wanting the minimum volt ampere rating. You must understand this. This will not be specified also. So when they are wanting the volt ampere rating, first calculate the current, because to calculate volt ampere rating, you need two things, current and voltage. That's why we are calculating current. But to calculate the voltage, it needs to be come from the power balance. So apply power balance. And what type of load is this? This is a leading kind of load. So now you see, if you apply power balance, first thing you need to consider, you do not need to include the compensator in the active power balance equation, because this is a self-supported DC link. So it will not participate in the power balance, active power balance equation. That was the key thing. Okay. So when you write the active power balance equation, you need to include the source, which is the Vs into Is into cos of beta. Beta convention we are using. Beta is the source power factor. Theta is the load power factor. I will write for you. Source power factor. Theta, whatever, when we write theta, it is meant to be indicating load power factor, which is the angle between VL and IL. Beta, angle between Vs and Is, or IL, because Is and IL are same for such configurations of series networks. And the remaining delta angle is the angle between source and load PCC. So now you write the power balance equation. The supplied active power from the source is to be dissipated by the resistance of the impedance, impedance, and then IL square into, because Is and IL are same, I can write Is only, into RL, because this holds since triple SC is having a self-supported DC link. So no active power supplied, I can write by it. So this was one equation, okay? And second equation, simple, this is Is. Okay, these all equations are after compensation, okay? You must understand. So when I write Is, this means after compensation. Okay? So I can write it as like this. This will indicate that it is after compensation. And sine beta equal to Is square into Xs plus Is square into XL. XL I can write because it is lagging kind of load, having inductive nature, right? So XL I write plus, because this side we always write absorbing reactive power or active power is absorbing. If it is delivering and you write it on this side, it is minus, just like we did in the previous one. So let's put the values. So VS is 230.94, IS is, you just plug it the values. What is it? 7.69. Beta is unknown as usual, and IS is again 7.69. RS is given in the problem to be 2 ohms. This is the supply side. Source impedance I can tell, source resistance, and load resistance is given in the problem 24 ohms. IS I calculated 7.69. So from the first equation, you are getting all the terms. Because you don't have VC, it became easy for you. Earlier problem you were having VC, one VC term, extra term here from the compensator. Now the compensator is not participating in the active power balance. That's what we are gaining is that using one equation we can directly calculate beta. No need of plugging the quadratic term. So it was becoming complex. So that way we are simplifying the problem, and in the exam it can become easy for you. It can just calculate in one line. Just divide and you know all the values. So what is it coming? Just in one line we can do VS IS cos beta. This is the equation. And what is IS square RS plus RL? RS is 2 and RL is 24. So 26. 26 into this IS square. What is it? 7.69 square. So what is it? 1537. So you just do cos in beta is what? Beta is cos
30,
inverse
30 degrees.
30 degrees. Yes. So just let me do once so that everyone can see. 1537 and VSIS you know 30.94 into 7.69, and you take the cos inverse and you obviously you get 30 degrees. Yes, correct. So it was like that. Cos inverse of 0.86 it's was. So beta was 30 degree. As soon as you know beta, no need of quadratic equation because you can plug this here. Same values you can plug in here. And IS you know, you plug it in here. XS you know. What is XS? XS is J4. So mod XS is 4. This 4 ohms. XL what? XL is 18 ohms. Again you can calculate and no need because you are already having. But in this equation I forgot one thing. We need to include the compensator also. Do not tell me. EC into IS into what I will write? Sine of theta. This we forgot. The compensator will push the reactive power, right? So we need to take it in the reactive power balance equation. This is reactive power balance equation. The compensator we need to include in the next equation, right? Because compensator was not participating in the active power balance because it was self-supported DC. But in the reactive power equation, we need to include the compensator. And why this is theta? Can anyone tell me? Angle between the voltage inducted by the compensator and the current is theta. Why? Can anyone tell me? Remember the phasor diagram? It is same as the load angle, load power factor angle. Why? So you draw the phasor
Because
diagram.
we are not doing any power factor correction. We are
Correct. Correct. It is minimum volt ampere, so minimum voltage injection in line with the load voltage, and hence you get that. If you remember the phasor diagram, also it is easy. Just see if we have VS and then we have IS or IL after compensation ITEL. So it was like this, and you have the voltage across the load to be this, but you want it to be more. So you push the voltage in line with that of the load voltage to get minimum volt ampere rating. So that's why theta of the load and theta of the compensator will be same. Voltage across the compensator and current through the compensator I'm talking about. So that will be theta. So just theta you know. Theta is coming from where? If you want to calculate theta, what you will do? You will do just tan inverse of that load. Z is there. Na? 24 and 18. So 18 by 24 you can do. What is tan inverse of 18/24? Is 36 degree. So plug it in here. Where? This one. And beta you already calculated as 30 degree. So now you can calculate this VC. This one. Why VC? Because you need the volt ampere rating. So volt ampere rating needs two things. That's why we are putting the value of all the other terms. So theta was 36 degree. We just calculated. So theta you can plug in. And if you want to do this equation here only, you can do. But otherwise, I will suggest you to do it as homework, because I will have to cover more problems. So because we are going to end the UPQC problems also today. I can write the answers for you. Just check. If you face any problem, you can just write in the group or just mail me. So I will write the answers for you. Okay. So after solving the quadratic equation, you will get VC, that is compensator, that modulus, to be 54.14 volts. And with this, if you calculate the, now if I tell you this, we solved it using the single phase equivalent circuit. Now one was having the problem in the calculation of three phase power. So I'll tell you the voltage, that is what kind of voltage this is. He was having doubt, he can tell. What is this voltage? Line voltage or phase voltage? Someone was having problem. So whatever power balance we did what power balance? Single phase power balance or three phase power balance?
Single phase.
Single phase. Assuming also many assumptions are there that this system was balanced also. This assumption was inherently there. So power balance, this was single phase. So everything we did in per phase. As you also can see, while doing this equation also, we reduced the line voltage to the phase voltage. So every parameter we are getting on line, not the line parameter, they are the phase parameters. So this VC was also coming to be the phase voltage. Now, when you want to do the power, calculate the power rating for such a three-phase system, so you do 3 into V phase into I phase. So 3 times V phase is 54.14 into I phase, I line, that line current 7.69. So 7.69, that was going to give you 1250 volt ampere. Okay, 1250 will be the answer. So I write here the answer to be 1250 volt ampere. You will get this. Solve and just check. So moving on to the next problem. Okay, next we start the UPQC. So just read the problem. We have 3 to 4 UPQC problems. After that, we can move on to the filters. Okay. We will be covering the filters from the next week. We have many problems. So starting the filters. But before that, 3 to 4 UPQC problems still needs to be done. So just read the problem, and then when you are done, you just let me know. So note that this is UPQC P. Now you must have known that what is UPQC P. It can only, the DVR in that UPQC can only inject the voltage in line with that of the, that is inline voltage, not quadrature voltages. Only the inline voltage it can inject. So there is a voltage sag, and in that condition you are asked to calculate the current rating of the statcom, right? So how will I do this problem? Using power balance, okay. Because I told you that I must have also done one problem like this, but not together. So let's do it. So voltage sag at supply side, okay. What does it mean? That your source voltage is having a sag. So what was the initial source voltage? So this is a single phase system, please note, okay. Now the load is designed for 230 volts, 50 hertz, 23 ampere and 0.8. This is the load rating specification that they are giving you. But they are also telling that the regulated voltage should be 230 volts. This is where this is at that load PCC. We drew the single diagram, na? In that load PCC they are talking about. But the sag is happening where? Sag is happening at the supply side. So if you want to visualize this problem, you can just draw a small diagram just for the first time, a single phase equivalent, maybe a network you can draw. So this was the so while solving this problem, they are not telling you anything about the source impedance. So for the time being, you can just get rid of that. Okay. So this was the PCC, I can tell, the source side node. And after that, you are connecting this device. So there is a series compensator sitting here. So this can be assumed as the device, and there is a common DC link also. The common DC link, and then you have the D-STATCOM, which is connecting in shunt. So after that, here you have the shunt, and then you have so a back-to-back converter kind of thing is there, where you have the DVR as well as the D-STATCOM sitting there, and both are sharing their powers because you have to inject some power also. So we can do power balance in this loop. So I'll just show you how to do these problems and what is the basic principle of solving these problems. So tell me one thing, why is the D-STATCOM installed? So D-STATCOM is connected in shunt, so it will mitigate all the current quality problems. And the DVR of this UPQC is actually installed to tackle all the voltage quality problems. But there is a restriction that is a UPQC P type of device. Okay, it can only inject inline voltages. So that is the thing. But now you have to calculate the sag. What is the sag? Sag is happening where this node. There should not be any effect on this node because load should continue to get that 230 volt of rated voltage. Okay. So what is the sag? You just calculate first. They are telling 20% sag. So 1 minus 0.2. So 0.8 into 230, what it is? 184 volts. So this is the voltage of the supply system after the sag has happened. Okay. So now the load power you calculate. The load should continue because assuming that all the compensators are working as they are designed and we have achieved the functionalities, then the load PCC should have the 230 volts and load should continue to receive its power. So this load power is not changing. That is the basic principle. So what is it? 230 volts into 23 amps into 0.8, right? The active power I am calculating. And what is the active power? Just let me calculate.
4232.
4232. Now this is not going to change. Why? Because the DVR is ensuring that the supply voltage, that the load voltage is regulated. Okay, this is its job. So the load is continuing to receive 4232. Whatever it was for it to get rated power. So this is 4232. Now you calculate what is the amount of current that is being injected. Because one thing I tell you, the D-STATCOM, whatever the D-STATCOM RMS current they are asking, the D-STATCOM RMS current will have two components. One component is for the reactive and another component is for the active. Why the active component is coming, I will tell you. But first understand that the D-STATCOM will mitigate all the reactive power requirements of the load. So this is its principal job. Why? Because it wants to mitigate the reactive current requirements of the load such that the supply side do not have to push additionally some reactive power. This is done to ensure unity power factor operation at the AC side. There is the supply side. So if someone is supplying the reactive current requirements of the load, then the supply will not have to push that reactive current and you will get unity power factor operation at the supply side. Now, since the load reactive power demand has to be mitigated because there is some reactive power demand from the load because the power factor is 0.8. So it needs some reactive power also. So that needs to be supplied by the D-STATCOM. So it is easy to calculate how much the D-STATCOM will push the current because see D-STATCOM, we can write that IDSTQ and IDSTA. I can write like this. Some reactive component of the current and some active component of the current. Now, how you will calculate the reactive component? You need to understand first that equation will come. D-STATCOM meets reactive power demand of the load. So, what is the reactive power demand of the load? QL is 230 into 23 into 0.6 What is it coming? 3174 volt ampere. Okay, these watts. So 3174 is the reactive demand of the load. So how much is the current for to meet this reactive demand by the D-STATCOM? 23 into 0.6 you can also do, or you divide by the voltage, same result will come. This when you divide by the voltage, powered by the reactive power by the voltage, reactive current will come. So this has no meaning. This will go away. Only 23 into 0.6 will remain. So 23 into 0.6, which is the reactive component of the load, is supplied by the D-STATCOM through the shunt path. This path. Okay, I will mention it by a color. This is the shunt path. This is pushing that reactive current. So by KCL, this side is maintaining unity power factor operation. And since this is a UPQC Q, UPQC P, so the inline voltage will come. No reactive power is coming. So the AC will see only the UPF operation. So the shunt path will push the reactive current of the load. How much is IDSTQ? If someone asks you, what is that? 23 into 0.6. The reactive component of the load that will supply the D-STATCOM. Okay, it's reactive component. So I can calculate 23 into 0.6, only 13.8. This much is the reactive component of the D-STATCOM. Now I tell you what is the active component of the D-STATCOM. Now for that you need to understand that load is continuing to get its power. Why? Because the voltage is maintained at the load PCC. But what would have happened if this compensator was not installed? That sag portion, due to this sag portion, some amount of voltage was lost. So this 230 into 0.2, this much voltage into some line, into this current, whatever is the current, the load current is 23 amps. And I can tell the active, so 23 into 0.8 into V. Now I will write it in the new, because this is creating confusion, I think. So see what I am trying to tell. So load power, active power, is maintained constant, right? This is the basic principle of calculating that D-STATCOM active component, IDSTA. So I can write that due to that drop in that voltage, due to the sag, if that was not mitigated by the DVR, that much power I can tell, then the load power would have been decreased. Because load voltage, if you decrease, the load power would have decreased due to the sag condition. Now that the DVR is not letting to do. The DVR is not allowing that drop in voltage. So from somewhere it is getting that power to push that amount of voltage, because you cannot push reactive power there. Because if you had pushed reactive power, that active power demand would not have been satisfied. Because during the sag, when your voltage is 20% dipping, that the power for that 20% voltage of the load would have also dipped. But their DVR is not allowing that dip, means that from somewhere it is getting that power. So from somewhere it is getting that power means that the D-STATCOM is actually through that DC link, some source is active source is sitting there, which is allowing to push that part of power to compensate for the sag in form of the current. Because your voltage at the supply side will be stiff at a sag voltage, but you can inject that voltage to the DVR after the supply node, then that sagged power would be compensated and the load power will be same, whatever it was before. So what I'm trying to say is that if you can do the power balance, then you can see. So what is, so VSAG? VSAG is some percentage, maybe X% of V supply. And I line was there. So maybe IS can be there. So I am talking about this supply current. Okay. I am drawing it once again here. So this is the supply. This is a supply node. After that, the DVR is sitting, and you have the capacitor. Again, that D-STATCOM is there and connected at the shunt. And then you have the load. This is the IL. This is, I can say, VC, whatever the voltage it is injecting, and this is IDST, and this is the supply current, and this is also the supply current, same series it is flowing, right? So now I can write X% of V supply is the sagged voltage, whatever the sag was there. So the power for that, let us calculate. So multiplied by IS, because note, at the supply side, it was having unity power factor operation. So IS and VS were in line. So I not include power factor, right? This will give me the active power. So this much active power would have been lost if the DVR would not have been injecting that voltage, VC. So obviously the DVR would have been injecting that sagged amount of voltage such that at this point, the voltage becomes same as that of the rated. But the power due to that needs to be also injected by the DVR such that the load continues to get continuous power, same power. So for that, the DStatCom needs to push that current. So whatever is happening in this side should also reflect at this side such that everything is happening in sync, such that the power balance is taking place. Because here the DVR has done its job, voltage is maintained. But this current, whatever current is needed to inject that voltage needs to be pushed from the DVR only because, DStatCom only, because that source is sitting there to push that particular amount of power. So I do the power balance. What is the power balance? That power balance at the supply side and power balance at this side, whatever the DStatCom was given. So I can write like this, that X% of V supply into IS is the power that the DVR is injecting. So this should be equal to this one, this IDST, that is DStatCom active component, into your voltage, PL, I can write. So this much, these two should be equal, because whatever was the sag voltage, amount of sag I can tell, that voltage multiplied by the supply side current, unity power factor, because supply is having unity power factor. That amount of active power needs to be pushed from somewhere else, so that loads get continuous amount of power. So this is IDST A. So what is this happens by power balance? Okay, do power balance at this node and this supply side. So, sorry, at the compensator, this one, the amount of voltage that it needs to inject, because these two are only connected, na. So that I am doing the power balance at that loop only. So IDST A is calculated as 0.2 into our supply voltage was 230 into IS divided by 230. So what is it coming? .6 amperes. So what is IDST actual? It is IDST active plus square plus IDST reactive square whole root over. This is the net current rating. Okay. So 4.6 was the active component and the reactive component is equal to 13.8. What is it coming? .55. So this is the current rating, right? So remember, while calculating the active power, because some active power is required, you need to balance that power to calculate the DStatCom current. I hope this is understood, right? If you have any doubts, just ask me. So understood why we are writing this question, because this is very helpful. If no one understands, then I will explain again. Okay. So just remember that particular sag would have reduced the load power rating or reduce the load power. We don't want that. We want to maintain the voltage. So for that, some power, additional power is required even during sag condition. So if you just realize that if some passive elements are there and some current flows through those passive elements, voltage drop happens like a resistor. Voltage drops. But if the reverse happens, like this, current is flowing in this direction and voltage is like this, which is exactly the same case as in this problem. The voltage is less in this side at this supply node, and at this node the voltage is more. So negative voltage it needs to inject. So or negative voltage, maybe you forget. You just assume that some voltage it needs to add, because this is V supply. You assume KVL. This is V supply gain, and then again some voltage is injected. How much voltage you need to inject? The sag amount of voltage, because voltage is now 0.8 Vs after the sag. If you inject 0.2 Vs, then it will be Vs. But for that you need some power. Why? Because this power is not absorbed. This is delivered. If current and voltage is like this, then it behaves as a source, not as a load, because current is coming out from the positive end. So it needs to deliver that power. So from where it will get the power? It will get the power through power balance. If you apply power balance, you will get that whatever current the D-STATCOM will push, it will just convert it to the amount of voltage and inject it. This is its job. Okay. So that's why we are injecting, we are trying to calculate what amplitude of current that needs to inject. And accordingly, we can just determine what is the power. So all these are happening through proper control algorithm, right? It's not happening automatically. There are all the gating pulse are getting generated from the sense signals, and then comparing it with the reference signals, and then we are commanding that you just give this amount of gate pulse, and then accordingly the functionalities will happen. So that is how it is happening. So the next problem you just see. Now we are solving the UPQC problems of different nature. Be careful, because they may appear to look same, but they are actually not. Okay. So this is the UPQC queue. So just see. Also, this is a three phase. Okay. These are the points that you need to note before just seeing the problem. Just whatever I am asking you to read the problem because of this only. You just need to see what are the differences. I need to highlight also why the problem is taken. And also you are using it for what? For reactive power compensation at the such that your AC mains is operating at unity power factor. So these are the 3-4 conditions that are happening. And in meeting those conditions, you are asked to calculate that when there is a voltage fluctuation means sag of 20%, because minus 20% is there. Minus 20% fluctuation means the dip is happening. So voltage dip, and base voltage is 400. Then they are asking you to calculate the D-STATCOM RMS current rating during the sag condition. So draw the phasor diagram, because till now we have not calculated the in that condition that what is actually happening for UPQC Q. I am telling, because UPQC P was easy, you were calculating by power balance, but UPQC Q is what? It only injects what's the reactive, that is quadrature voltages. So there is no question of active power. Please understand that if you have UPQC P, it needs active power to operate, but UPQC Q can only inject the quadrature voltage, which does not need any active power. So these are the important points. So how will you draw the phasor diagram? Let's see. Okay. So what was the scenario that initially you were having Vs at the supply side. Now Vs dropped to 0.8 Vs because 20% sag happened. So now what is the voltage? If someone says this is the voltage, this is the new voltage. So I draw it by Vs prime, which is 0.8 Vs because of the sag. In this condition, you want your UPQC Q to inject quadrature voltages so that you can again attain Vs amplitude of voltage at the load PCC. So if you draw the circle, can you see how where at which point it will come? Anyone? Such that Vs is met. You cannot inject inline voltages, please remember, and you cannot inject any type of voltages. You can only inject quadrature voltages. So either up or either down. How will you inject? Please note what is the nature of load. Nature of load is what? Lagging or leading?
Lagging.
Load is lagging of lagging nature, right? So your current will be obviously lagging the load voltage and also the source. So whatever voltage you will inject, please note that that current should lag that voltage. So just see, you have two paths to go. in order to make the load voltage actually equal to the rated as to the supply. We have two ways. Either you can go in this direction, up or down, because you are bound to do that because no active power support you will gain from the converter, because there is no source actually sitting there to push that active power. So somewhere from you have to inject reactive power only. You cannot inject even some voltage at an angle, because for that also you need some active component, but there is no active source there. So you cannot get help of that. Otherwise, you would have minimized the volt ampere rating. But still in this condition, the UPQC queue, with the UPQC queue, you just want to provide the reactive power compensation, as well as you need to maintain the voltage at unity, right? So your current will be obviously after compensation in line with the, that is the source current will be in line with the supply voltage. IS I am talking about, and IL will be lagging the load voltage. So that is the scenario which is known, that after compensation your load voltage, whatever is it at the load PCC, will be same as that of VS in amplitude terms, and your source current will be in line with the supply. These two factors are known. So during the and also there happen the sag. So during this condition, which way you will go, up or down? Just tell me that.
Up.
Yes, up, because if you go up, your voltage will be like this. I'm talking about load voltage, and your current, source current is like this, and your load current will be what? So this is delta, right? The angle between those two voltages, source side and PCC side. And you know your nature of currents also. So load current will actually be lagging. So this you can calculate actually what is the angle delta, because this you know, this how much VC you need actually, and this voltage also you know 0.8 VS. So tan inverse VC by VS, that is VS prime 0.8 VS, will give you delta. Any doubt up to this? Yes, hello. Yes, any doubt up to this? So now we need to calculate the D-statcom RMS current rating. So phasor diagram we do because I needed to show you that how the voltage it should inject. Okay, such that the voltage is maintained at the rated. Because if you are able to maintain the rated voltage, and also you need to understand that you are maintaining unity power factor. So IS is like this. I'm also indicating that this is IS because it is unity power factor operation. You can push the voltage in quadrature to that of the source, and then your load voltage will be equal in amplitude because it is hitting the circle, right? So now tell me how to calculate the D-statcom current rating. You first calculate the load. What is the type of load? So load power you calculate. So it is given 60 kVA, right? So from that load current you can also calculate. So calculate the load current. Just calculate the load current. If this is the nature of the load, and after compensation it has achieved 400 volts, so calculate what will be the load current, because it is a lagging kind of load. So whatever, if it receives the rated voltage, it will draw lagging current. Okay, so you need to calculate that current. So just calculate what is the load current. If it is 0.8 power factor lagging load. So what is the right like this? I can write like this: S by root 3 into VL. This is I line. So what is S? S is 16 to 10 to the power 3 kilovolt ampere. Please note it can also be written as kilowatts. So then you need to convert or use the power factor. So but here I can write like this, that it is 16 to 10 to the power 3 and having an angle of root 3 times VL. VL is 400 volts. So what is the load current coming? Sixty into 10 to the power 3, right? Divide root
86 amps.
yes, 3 into 400. 86.6, right? So this much load current will be in lagging condition with that of the load voltage. Load voltage is like this at an angle delta ahead of the supply if you assume it to be angle 0. So now if I ask you to calculate what is, let us also calculate the PL and QL. What is the load power rating? 60 into 0.8, right? So what is it? 48, right? Kilowatts. And this is 36 kVA. The load is lagging in nature. It is already given, right? So now you calculate what is the voltage that you, now what happens, the sag has happened, okay? So voltage sag has already happened. So this voltage, do you know? Can anyone tell me? Is this voltage known? VL? After compensation I am talking. Mod VL. Let it be mod VL only. Mod VL is known, right? Because it is after compensation maintained to rated, right? So what is the value? It is given to be 400 volts, right? Okay. So 400 volts. So VL is 400 volts. And what is your this VT? Or you can write this as, because I can calculate VC using the triangle. So let me write what is, I can write VS prime because this is after sag, right? So what is it? 0.8 into VS. VS is what? 0.8 into 400, 320. So you can, let us do it in per phase basis by root 3 you do. So that will be easy, okay? So VC is what? Because why per phase? Because it is a 3-phase system. So all calculation we need to do per phase. Otherwise, when we do by 3-phase, then we have to divide by 3 or root 3 accordingly if we take phase or line. So do everything in per phase such that when you calculate the current, line current and phase current are same. So you need to take the phase voltage such that the per phase power we can take and then determine the current accordingly. So do all the calculation always in terms of per phase. Otherwise, while determining the current, it will be problematic. Okay. So VC is root over VL square, because what is VC? You can write na VS prime plus VC equal to VL, and so VC is VL minus VS prime. And if you do it in phasor, obviously why this is phasor addition. Okay, so you can just find that VS, you can just write like this. Okay, VC square plus VS prime square plus VC square. This VC, this much, this is VC equal to VL square. So VC is what? Root over VL square minus VS square or VS prime square. So VS prime is what? In terms of amplitude only. VS prime is 0.8 into VL only, because VL is VS rated. So only the amplitude we are talking about. So you can just take it common and 1 square minus 0.8 square whole root over. Like this also you can write. So what is it coming? Voltage. So why we are calculating voltage? We have been asked to calculate only the current. But if someone asks you to calculate the volt ampere rating, then volt and current, both you need to have. So compensator voltage calculating method is for UPQC Q is like this. You just apply the triangle rule and then calculate the VC. Because you know that after compensation, your load voltage will be same as that of the rated. So what is VL into 1 minus 0.8 square whole root over? VL is just rated. Is rated. So rated voltage means you have 230 volts because 400 by root 3. 400 by root 3. Okay. 230 volts into root over 1 minus 0.8 whole square, which is 0.6 actually. Root over 0.6. Sorry, into 0.6. So it is around 138 volts. Okay. So VC, mod VC is 138 volts. Around approximately. Now determine how to determine the current for UPQC Q. Because previously in the previous problem you were using that formula of power balance. So no geometry you need to incorporate. But here you need to actually use geometry to determine because VL is like this at an angle. So from here you will determine IL, which I was asking you in the starting of the problem. Because IL magnitude you can write because only the amplitude you need to consider. But if you want to find the angle of IL also, there the geometry comes. Then the angle of on that angle you need to actually what is D statcom current, then I D statcom you need to determine because that at that node you need to apply KCL, just like the problems of D statcom we did. So at that load PCC point, you need to apply KCL. After you determine the IL with phase geometrically, because you need to apply geometry because angle, nothing will be direct. So all the angles will come and from there you need to subtract. So lot of calculation is there. So there is a direct method of calculating the D statcom currents for UPQC Q, which is directly you can write like this. So I will just mention here. So voltage rating you understood, right? How to calculate voltage. It is easy because voltage injected is quadrature. So you apply triangle and then you calculate. You know that the voltage, load voltage is rated. So load voltage minus your sagged voltage at during sag will give you the compensator voltage. Now for compensator current, you have direct formula with me. I then write it IDS because you have to use geometry in that case. Okay. So geometry will take time and we have the direct formula of the result. So you can just prove it and show me in the next or just send me your proof in the group also. If you want, I can also show you. But not here because it will be taking time. So first I need to cover UPQs. But if you want, you can just send me and I can just show you. So IDST for UPQC Q I can write. The current directly you can get. So I can write the formula. So this is, I can write in blue. So this comes just by from the phasor diagram. This result follows directly from the phasor diagram that we just drew and applying KCL at that node. So IL into root over 1 minus X. X means that percentage of sag. If it is 20%, X is 0.2. Just like in this problem. So this whole is within the under root, okay? Divided by 1 minus X. So now, if you want to calculate for this problem, then IL is known. IL, we just calculated IL, 86.6. Calculated. Root over 1 minus 0.2, which is 0.8. Now, what is phi? Phi is the load power factor, right? So, load power factor is known. Phi is, to draw the phasor diagram, you can just see phi is, yes, phi, you can, so the notation holds true for all the cases, right? So, beta is the source power factor, delta is the load, or I can write delta is the angle between. So all are angles. Angle. This is also angle. Source power factor angle. And delta is the angle between source voltage and load voltage. And obviously theta or phi, both can be used, are the load power factor angle. And how will you calculate load power factor angle? That is already given in the problem indirectly. If you can understand that 0.8 was given as the load power factor. So phi was calculated from there as cos inverse, sorry. So the screen got frozen actually. 1 second. So is my screen visible? Okay, I will just reshare. Yes, I think it is visible. So phi load power factor angle you can calculate. It is easy because 0.8 power factor was there, so cos inverse 0.8 it will come. It is easy, right? So now once you know the load, please remember these terminologies because they will be used very extensively while we do this kind of problem. So phi or theta, anything you can assume to be load power factor angle, which in the phasor diagram also I showed you multiple times. The beta also I showed. It is the source power factor angle. Power factor angle means the angle between the voltage and the current, right? The source voltage and source current, you find the angle to be that beta, and the angle between the source voltage and load PCC voltage delta, and phi or theta, anything you just assume to be load power factor angle. So where from you will get the knowledge of the load power factor angle? Load power factor angle you will get directly in the problem. It will be given from either the tan inverse of that impedance J by your real imaginary by real part. You can calculate that phi. Once you calculate that phi, you need to know you have to know the knowledge of delta. Now what is delta? Delta is for UPQC Q I am telling. Tan inverse V compensated by V load or V sag, that is voltage after sag. Voltage after sag, it is 0.8 times Vs. So delta is tan inverse Vc we just calculated using the triangle rule. Vc you always need, and then to calculate delta, and then 0.8 Vs. Vs is the rated supply voltage. So delta also you know. So phi you know, delta you know. Can you tell me what is beta from this phasor diagram? So beta is nothing but phi minus delta. But beta is already incorporated in this formula. Okay, so you don't need beta actually. If you know theta, if you know phi or theta and delta, then you can calculate. So you can just assume cos square phi. So cos square phi means cos of phi whole square. Okay, so 0.8 square. Cos phi is 0.8, right? So I just do 0.8 square minus 2 into 0.8 into what was delta coming? Delta we calculated.
38.65.
Yes. Tan inverse 138 divided by 230, right? Into 0.8. I will just show you. So if you want to calculate delta, it is tan inverse 138 divided by 0.8 multiplied by 230. So it will come out to be 36.86. So cos of 36.86 is again 0.8. So I am not writing it again. 0.8 only. And you have 1 minus 0.8, which is 0.2. Sorry, 1 minus 0.2 because x is 0.2. This is 0.8 only, okay. And divided by, this is whole thing is within the under root. And then you have 0.8 because 20% is the sag. X was 0.2. So 1 minus 0.2 is 0.8. To calculate this, you will get 0 amps. This is the answer. So you don't actually need any, if you want actually to attain that power factor which is already existing, why do you actually need the D-STATCOM? So this problem was formulated in such a way that the requirement and the existing condition both are same, for which you don't need the actually D-STATCOM to be functioning actually. It may be sitting there for, because D-STATCOM can be used for some dynamic condition. For the exact existing loading condition, D-STATCOM current will be 0. Because you are not putting any effort on the D-STATCOM. Whatever is there on the load side, you are achieving that only. You are wanting that only, I can say. So the D-STATCOM is not burdened. So that's why 0 amperes. But for
So one doubt. So here this cos 5 minus delta, how did you get it as 0.8? I'm getting close to 1.
cos of 5 minus delta.
Delta,
Yes,
yes.
it is 1. It is 1.
Yeah.
Yes, because phi and delta both are same, na? Yes, yes. So it is 1
So
only.
yeah, then in that case, are we not getting okay, there is one more 0.8 there. Sorry. Yes. Next.
It is gone, right? That thing is cancelling. Yes, it is 0.